Okay, good morning, everyone. So marks went up this morning for the midterm. Sorry that took so long. I don't think, besides one person who scored like a 97, everyone else really struggled on this midterm. And I think it was really clear to me that, like, the whole idea here is I know everyone's coming with different skill sets. That's why we have the assignments all posted at the beginning of the class, and the exam questions are drawn from the assignments. And a couple of issues that kind of really stood out. One is I don't think there was a very big use of external resources. And by external resources, I mean like the literature, sci-fi searches, trying to think things through, use of recommended textbooks. They're all available online. We actually have access to them through the university library for e-copies of a lot of them or equivalent ones. And like, this is a senior class, graduate class, so I don't think that is, it's not so much I don't think, it's that is an actual expectation of a senior or graduate class. It was just clear that wasn't done. And that being said, the questions can be done basically entirely with the notes. It's just you might want to confirm stuff using other sources. So there was that. I think in some cases too, there was an over-reliance on simplistic sources. So there was a lot of plagiarism from Wikipedia. The problem is Wikipedia has a lot of errors in it, and the errors propagated. So that results in very poor marks. I'm not making any formal motion here, because I don't think this will count as an evaluation for any student. But I do want to warn that there were clear cases of pure collusion and more beyond collaboration was collusion. It was almost exactly the same answers. They were the same wrong answers, but these are exams. You are supposed to do your own work. And in some cases, it was an example where a student might have been the one who came up with the answer, gave a more detailed answer. Other students provided very similar answers, but with less detail and clearly lacked understanding of what they were putting down. So I think there's a lot of issues with the midterm. So I would encourage everyone to take the time to go through the assignments, answer all the assignments in advance. There's nothing wrong with you having them all written out in a clean version, and you can more or less upload the answer if that turns out to be the answer on the exam. That is completely valid and fair. If the question comes up and you've already done the work, that's what matters. The whole logic behind these is I think the assignments cover what I consider are the learning outcomes of the course. And if you hit that, then you understand the material. And if you are able to do it in advance, that's fine. If you're able to do it in a 3-hour time period, bully for you, but that's not necessary. So I think in a class full of people with a strong background in synthetic chemistry, these would be fair questions to be asking for a 3-hour time period blind. I don't feel that's necessarily fair for this class with a much broader area of backgrounds. So that's why you have, 13, 14 weeks to get these together for the final exam. I don't really have much more to say about that. If anyone has any questions or wants to see their exam, I'm happy to, if you're on campus, if you're in Windsor, happy to give you back a physical copy. If you're not in Windsor, and only if you're not in Windsor, I will scan it and send it back to you if you request it. But I think in general, there's not a lot to take away from it. So what I want to do is I want to continue from, and so before we start, any questions or comments or anything on that? I think this is the 4th time I've taught this course. I draw different questions in the assignments every year. I've generally had, class averages, both of the undergraduate and graduate class around 60, 65. to 70 on the midterm. This year I didn't calculate the average, but it's definitely a failing average. It's 30% or 40% below where it normally is. And it's I've taught this remotely in the spring, basically the same way here. I I have no comment on that. Okay, so last class we left off discussing. I left the class with this question, which is basically, so if we want to make alanine glycine, and remember we always read these things N to C, we can notate it this way if we want, but we don't need to. It is by definition alanine to glycine from N to C if it's written that way and nothing else is indicated. And so that's this. There's a peptide bond or an amide bond between the alanine and the glycine. And then we use what I said is we can use, let's say we had a magic reagent that could snap these things together, and we had a 1-to-1 ratio of alanine to glycine. Would we get the structure on the left? Would we get the alanine glycine? If yes, why? If no, what do you get and why?
He said no, and because because the amine group in alanine is more basic, so I think we have guanine and glycine alanine, because I think the alanine amine will attack in this time.
So do you think the amine group in alanine is a lot more basic than the amine group?
No, not a lot,
Okay.
but
I
a
agree.
little bit.
And you're right.
Okay.
You're absolutely right. The alanine, because you do have donation, because this compound here is substituted, which makes it more electron rich, which will make this nitrogen more electron rich. So this nitrogen on alanine will be more reactive than the nitrogen on glycine. I'm thinking like maybe 2% more reactive, 1% more reactive. So what you're saying is we can get probably glycine alanine,
Yeah.
but you think we would get some alanine glycine as well?
Yes.
Anything else? Is glycine the only thing alanine can react with?
Themselves?
Yeah. So you're gonna get some alanine, you're gonna get some glycine, and then you're gonna get oligomers, right? You're gonna get what's like. Let's say there's let's say you have these 6 molecules together, and we want glycine and alanine to react together, but nothing's stopping glycine from reacting with glycine alanine.
Triplet?
We're gonna get GGA, AAG, AAA, everything, right? It's gonna be a complete freaking mess of everything. And it comes down to the fact that we have 2 nucleophiles and 2 electrophiles. Come on, I don't hide this. Well, I guess I should circle the whole carboxylic acid. So this is really problematic. Now, the ribosome has no problem with this, right? Because what the ribosome does is it takes the tRNA, it loads on one amino acid at a time, it's got structure, it's got order, it's an enzyme. It doesn't need anything more. It has a recipe saying you add these amino acids in this order, and it does that through templating the tRNA and then loading on each amino acid in turn using a standard condensation reaction. Chemically, not so easy. So what we prefer to do, of course, is protect. So ideally what we want, if we want to make alanine glycine, what we want is this. So what we're doing is, first of all, you need a lot of energy to make an amide bond by coupling carboxylic acid with nitrogen. You need to heat the crap out of it. And lots of other things can happen when you heat that hot. So what we want to do is we want to activate So we have an activated ester, protected acid, protected amine. Because then we have this very easy reaction. There's nothing else that can happen in this case. The glycine can't react with itself because its ester is not activated. The alanine can't react with itself because its amine is not available. So the only reaction that can occur is the glycine reacting with the alanine. It's not clear that's a G. Now make our new bond, and now everything, and you can't have trimerization because both our nucleophile, the amine, and our carboxylic acid are not active. So just like in carbohydrates, protecting groups are absolutely central to everything we're doing here. So yeah, that's necessary. So let's just consider one way of doing this, and we're going to do a very old school way of making these kinds of bonds. So we could take should do this in a different color. It's called a Bach group. One way to activate the carboxylic acid is to treat it with thionyl chloride, EMF, triethylamine, and this makes an acid chloride. I'm not going to go through the mechanism of that. We then react that with an amine, T-butyl ester, for example. So now what we have here is we have a activated leaving group, or the chloride, that activates that ester and makes it more reactive. Because a simple carboxylic acid is not very reactive at all. Sorry. There we go. So let's say I want to add another amino acid to this. And let's say for the sake of argument, it's a valine. I'm going to avoid side chain protection for now. So what we have here, of course, is we have glycine. And let's say I wanted to make VGG. What do I need to do?
Just debug the mean.
Yeah, okay, we need to remove the Bach group. We'll talk about that, how to do that in a moment, but we're going to just use trifluoroacetic acid. Make the TFA salt. And I'm going to actually sketch in what that looks like. The chirp butyl ester on the carboxylic acid will stay intact, theoretically. I'd pick something else in this case because chirp butyl ester actually comes off with TFA if you're not careful with the conditions. It's possible to do, but I wouldn't want to do it. Okay, so you've deprotected that. What else do you need to do now? Do I just throw?
Protect the V.
What do I need to protect? Nitrogen or oxygen?
Nitrogen.
Right. Because I need to protect this nitrogen, because if I don't, then it's going to compete with that nitrogen as a nucleophile. So I need to protect that nitrogen. We're going to run into, might as well introduce our, yeah, I'll do that. I'm going to introduce one of our star protecting groups. It's called FMOC. Use imidazole as a base. And we make our product. One of these days I will actually learn how to use this bloody surface. But it won't be today.
Is it possible to attack itself? If you have one equivalent of each, I mean.
Yeah, of course. Well, not immediately, but we're not done yet. Okay, so we've acted. So this is FMOC. Again, I'm just gonna highlight that maybe in a different color. Now we have this sort of 5-membered ring stuck between 2 benzene rings. It's a weird molecule. So, okay, so now we protected that nitrogen. We've deprotected that nitrogen. And now we need to activate this carbonyl. Because again, trying to make a bond between a nitrogen and a carbonyl that's not activated is really, really hard. For the sake of argument, we're just going to use thionyl chloride like we just did. We're going to spend most of the class today talking about ways not to use thionyl chloride. This is stupid. I have done this for making dipeptides, but I've never used it for anything more complicated. And so that's going to give us I have a really bad habit of dropping the hydrogens on amides. I'm sorry for that. So you sort of think of these things as almost being made of three components. There's protecting group on nitrogen, there is the amino acids itself, and then there's the protecting group on carbon. I think that's probably the way to go about thinking about these, or activating group on carbon in this case. And now we can treat A and B together with a base to get the product. Okay, so Ronaz's question was, can this thing attack itself? Well, if this it can't anymore, but if this nitrogen was not protected, it could definitely attack this chloride. There's nothing stopping that. Not intramolecularly, not within one molecule, but two different molecules of valine will be able to react together, no problem. So whenever we're doing this, what we note is we have this pattern we need. You can have a peptide, and this can be a single amino acid. It can be an entire peptide. It doesn't matter. And I'm writing amino acid, but this could also just be a single this could also just be an entire peptide. It doesn't need to be an amino acid. But we couple these together. Amino acid. I'm going to just draw a nitrogen of that. Then what we need to do is we can do one of two things. We need to deprotect. And we can deprotect either the carboxylic acid or the amine. Right now, there's no reason to do one or the other. We're going to see that we almost always deprotect the amine, and that's because of the way we make these things. But let's just do the carboxylic acid for now, because it's akin to what we had just done up there. Then we need to activate. So you turn that protecting group into that carboxylic acid into an activated and then we can couple. And then we just go around in circles. So we couple, we deprotect, we activate, we couple, we deprotect, we activate, we couple, we deprotect, we activate, and we build up our peptide amino and acid by amino acid. Now, the one caveat I'm going to note about this is generally there's a really awful bracket. Also a really awful bracket. I clearly don't know how to draw brackets. That's what I want to draw. So let's say we start with amino acid. And we have that. And then I can couple on additional amino acids. So we get a dipeptide. Then if I deprotect and then activate couple, get a tripeptide, and so forth. Now, let's say I want to make something that has a short amino acid, like a short peptide. So we want to make something with 11 amino acids. I start with 1, already ready to go. How many coupling steps do I need to do?
10.
Yeah. Okay, how many deprotection steps do I need to do?
Oh, well, 9.
I'm gonna still do 10 because I'm gonna deprotect the final thing as well.
Oh, yeah.
Every
right.
time I'm gonna activate couple, deprotect, activate couple, deprotect. So, because I want an amino acid at the end, I don't want a protected one at the end. So I need to do 10. So that's a total of 20 reactions. This is even chemistry, a math, and organic chemist can do. Okay. Now, so if the yield, so we have 20 steps. If your yield per step is 100%, what's your total yield over making the entire peptide? If every step's 100%. This isn't a trick question.
Trick saying there's no way it can be 100% or we
No,
missing
it's not.
something?
This is a theoretical question. I completely agree with you. But what's the answer?
If it's 100% for every step,
Yeah.
why is it not 100%?
Of course, it's 100%.
So why is it a trick question?
I said it was not a trick question.
Oh, okay. I'm sorry. Misheard.
Right. Okay. Let's say your yield is 75% per step. Now, that's a pretty decent yield. I'm pretty happy with a 75% yield. How do I notate that mathematically to calculate the total over the peptide?
I know this, I just don't know how to say it in English, but basically 75% times itself 20 times.
Right. Right? 0.75 to the power of 20. So it gives you 0.3%. So 75% is a pretty decent yield, but if you repeat it 20 times, you get 0.3%. So if you start with a gram of starting material, gram of your first amino acid. I'm doing this by mass. This is going to work. If I start with a mole of my first, no, you don't get very much. I'm trying to think of a simple analogy. It's not going to make things more complicated. You don't get very much. Even if you're 90%, this only translates into 12% overall yield. And 99%, you're like 99% sounds great, only translates into an 88% overall yield. 82%, sorry. So we have a problem because this is just for 11 amino acids. Like that's about the shortest you ever want a peptide to be. Most peptides, as we noted, need to be at least 5 to be really peptides. And most things don't recognize stuff much under about 13 amino acids. And sometimes you might want to build something that's 100 amino acids long. Like if we took 99% and we raised that and we pretended it was for 100 amino acids, that would be 0.99 to the 100. Not even sure if my calculator is going to be able to help me with this. It's not bad. 37%. But that's if every step was 99%. Sorry, that's not 100 amino acids. That's just 50 amino acids. If it's going to be 100, you actually need 200. Because each amino acid needs both a protection and a deprotection. %. And let's not even try and guess what that would be if we're at 75%. Actually, that's 0.75, basically 0.75 to the 200 equals 0. Because it's just then to at least 10 decimal places. So this tells you that if you're going to make long peptides, you're going to need really high yields. Because if you don't have really high yields, you're not going to get anything out of it. Like yields are always important. But they're even more important when you have these kind of linear syntheses. Because you just deplete your material so quickly. Those of you who carried out short syntheses will know that even then it's kind of depressing when you start with lots of material and as you go on you run out of stuff. And there's no simpler way to do it. Like we can't reduce this problem any further. We need to activate, couple, deprotect, activate, couple, deprotect. There's no way around that unless you're a ribosome, and you're not a ribosome. So we need very, very, very high yielding reactions. And what that means is our activation coupling needs to be really, really high yielding. Our deprotection really needs to be really, really high yielding. So where we focused on protecting groups in the carbohydrates was saying we want to deactivate functional groups as our primary function. And it was important to get selectivity and all that. Now our shift is from putting them on to taking them off. We want taking them off to be almost 100% yield because we need it to be really, really high yield. Otherwise we lose everything. So our goal is not so much to make putting them on easy and make selection easy, which is what our goal was with the carbohydrates. Our goal now with protecting groups is to make sure they come off really easily when we want them to. And that really limits the number of protecting groups that get used in peptide chemistry, because there's a lot of protecting groups where, yeah, it comes off okay, it comes off like an 80% yield, but that's not good enough. We need 99 plus. Okay, so we're going to start by talking about the coupling agents, though, not the protecting groups. So I sort of showed the thionyl chloride earlier. The nice thing about thionyl chloride is it's easy to do on massive scale, but it's the yields aren't great. So this is kind of a general scheme for basically any peptide coupling. we often activate the ester first, and so it's activation followed by coupling. We're going to talk about what DCC is because that means absolutely nothing. DCC is dicyclohexyl carbodiamide. What the hell is that? What's that? Okay. So immediately we should be looking at that and thinking, that does not look super happy. Nitrogen doesn't love making double bonds with anything. All nitrogen really wants to do in the end is make a triple bond with itself to make nitrogen gas. And what we need to keep an eye on is thinking about the other thing that nitrogen, the other endpoint for nitrogen is a urea. You know, when we fix nitrogen, we're often fixing it into ureas. Ureas are kind of the endpoint. It's this diamide thingy, and it's just stupid stable. So if we think about what we want to do with this is essentially what happens when you add water, right? 2 hydrogens, an oxygen. Obviously some electrons are doing some hokey pokey fancy business here, but essentially we are adding water across carbodiamide to make this happen. Except for doing it with the carboxylic acid, because what we really want to do is we want to strip away water from there and there. Because you remember what we're doing is we're doing a condensation reaction. So the carbodiamide is acting as a mediator of that condensation. So in producing water is, thermodynamically favorable. But what we're doing is we're kind of trapping the water as it's formed, and this is massively thermodynamically favorable. We're never actually going to see any water in here, but it's always a good idea to keep in mind that all peptide coupling needs to produce water or trap water. And so we're formally trapping water. So what's happening is we have a carboxylic acid. Unsurprisingly, carboxylic acids are acidic. It's kind of in the name. And amines, nitrogens are pretty basic. I'm going to shorten the cyclohexyl ring just to psi. Now thinking about the product, should be reasonably straightforward to draw that arrow. And oh look, we've added the oxygen to the carbon. So we're starting to think about how we can expel water here. And we've added 1 hydrogen here. This is our activated ester. We know what we want to do is we want to use this nitrogen to grab a hydrogen. And as soon as we do that, this oxygen is going to want to make a double bond with that carbon, which will then really, really weaken this oxygen carbonyl bond, which will make it susceptible to attack. And so that's what happens. In the presence of an amine, a primary amine generally. This does work with secondary amines as well, not with tertiary amines, which is why we use triethylamine as our base. You don't technically need a base for doing peptide couplings with carbodiamides, and we'll see why, but it often gets chucked in to accelerate the reaction. Carbonyl opens and closes, breaks the oxygen-carbon bond, generates a new oxygen-carbon double bond that we want from the urea. We need to break a bond, so we push electrons onto nitrogen. And I'm just going to draw in this top corner. I'm sorry, all over the page here. Shouldn't have done that. No, I'm going to draw on a new page. Sorry, I just need to create some more files. So we're going to have the nitrogen attached to this thing, and then we're going to look like we're going to be generating our urea. So if we have, what color is this? Okay. So we have that. We have our now nitrogen. I drew that wrong. Now, of course, this can just clean up that extra proton. That's why you don't need a base. Just note that the nitrogen urea acts as its own base. Every hydrogen that came into this is accounted for. So we make the urea. You don't normally worry about side products like the ureas, but I'm just noting them because I think it's important to keep an idea of why these reactions happen. And a driving force for this reaction is definitely the trapping of the water and the formation of the urea. So there's a bunch of these that get used. We've just seen DCC, so this is now dicyclohexylurea, DCU. So it's not a carbodiamide, it's now a urea. We also see two other main reagents. One is DIC, which I'm sufficiently immature enough to enjoy. And then the other one is EDC. These three DIC is definitely more reactive than the dicyclohexylurea. It's normally a lot better. It's the isopropyl groups improve solubility, and I don't fully understand why it's better. It always works better. And EDC is a little bit weird. So the advantage of EDC is it's easier to remove by acid workup following a reaction. Any ideas on why that is? After a reaction, of course, you'd have the urea.
Because the what's that? Is that amine or
Yep,
because that's very basic?
right. So easy to protonate. Easy to get into your aqueous layer. So if you want reactivity, you tend to use DIC. If you want easy removal, because it's becoming a pain in the ass, you use EDC. If you want to use something cheap, you use DCC. DCC is also the safest of the three. So if I tell you that these are incredibly toxic materials, you do not want these on your skin, you do not want to ingest them, why would that be the case? And their mechanism of toxicity is?
Because they're so similar to urea, kind of.
The ureas are fine actually. It's the carbodiamides that are really toxic.
Yeah, because they're so similar. So, which is it's like how carbon monoxide carbon monoxide works. It's toxic because it's so similar to
Oxygen.
yeah.
No, it's not in this case. It's a good idea. I like that idea, but think about, as I said, we didn't need to have triethylamine in there for them to do their chemistry. So all you need is this thing to couple carboxylic acids and amines together. You want to try again for why they're toxic? You're thinking too specifically, I think.
I'm trying to process what you just said. No, my mind's like it tries fast now. It doesn't work anymore.
I feel like I'm walking through a fog this morning. I don't know what's going on. So I'm sympathetic. So you've got a lot of free amines and carboxylic acids in your body. Every single one of your proteins terminates in an amine and a carboxylic acid. Most of your proteins have glutamic acids and aspartic acids on them, which are acids, and most of your proteins have lysines on them, which are amines. If you get some DCC in you, you will randomly start cross-linking proteins together, because some regulatory protein is going to cross-link with an enzyme because they both have, one has a carboxylic acid that gets activated by DCC, and the other one's got an amine. Boom, bond formed, and now you have proteins that should not be attached together. And that can lead to systematic toxicity. It can lead to protein malfunction. It can lead to death. The good news is your proteins do turn over relatively quickly. So if it doesn't kill you immediately, you're fine. There's no long-term effects from DCC. It's not going to cause cancer. It's just if you get enough of it into you at any one time, you will die quite rapidly because your proteins will all start cross-linking. So don't drink the chemicals. The amount you'd have to take in is actually quite considerable, but you don't want to be. Why play that game? Try and keep the amounts of really toxic things as low as possible. It's just generally a good policy. And this is the same problem with all coupling agents. So it's not like I'm going to go like, oh, this one's safer. No, they're all really, really dangerous. The other big class of these things that we use are the uraniums. So those are the carbodianides. Now we're going to just quickly discuss the uraniums. Which sound like it should have something to do with uranium, but they don't. These are weird molecules. There are 3 of them that we're going to discuss. They're all related. You just take a look and go like, that is not, should not be a thing. These are all obviously very closely related. With very minor changes in structure. That would have been a major change in structure. These are called HBTU, HCTU. The B stands for benzotriazole. The H is hydroxy. So it's hydroxybenzotriazole uranium. This is still hydroxybenzotriazole uranium, but it's got a chloride, so we stuck the C in for the chloride. But still benzotriazole chloride. And this is called HATU. And this stands for azo, because we stuck in a nitrogen. These names are stupid. What's really convenient though is A, B, C. There's no HDTU yet. Though, actually, you know what, I'm sure there is, but probably somebody invents it and nobody else uses it. These have various benefits. So HATU is the most reactive, HCTU is in the middle, HBTU is the least reactive. But it's also the cheapest. So there are reasons why you'd want to use HBTU over the other two, or not use HATU, because it's like, why wouldn't I want to use the most reactive one all the time? Side reactions, that's why. And we're going to see what are the major ones. So HATU can sometimes be too reactive. Mechanistically, unlike the CDIs, or if you think about the carbodiimides and their mechanism, we're using a carboxylic acid to do this attack. Theoretically, water can do that attack too. So when you use a carbodiimide, you want it dry. You don't want any water in your reaction. When you use a uranium, you don't care about water. You can do these reactions in water. Water doesn't matter at all. So these are very flexible. You do need a base now. And the universal base for these is DIPEA, or Hoenig's base, or diisopropyl ethylamine. We'll draw it out in a second. You do not use triethylamine. These react too rapidly with triethylamine. I'm just going to use HBTU and DMF, just as solvent. Why? Because DMF dissolves everything. And one of the other big reasons is DMF. I'm just going to draw the product of this. For those of you who don't know. DMF has an amide bond in it, and on the idea of like dissolves like, DMF gets used a lot for peptide chemistry because it does dissolve peptides really well, and it prevents peptides from aggregating and sort of folding back on themselves, and making really strong hydrogen bonds with themselves because they can make it with the solvent. So DMF tends to be quite favorable for that. That's why we see so much of it as a solvent in peptide chemistry. Note, this can all be open to the atmosphere. I'm paranoid, so I still do these under nitrogen, and I do them dry. They don't need to be. That's what everyone tells me. I don't trust everybody. I still do them very, very carefully because it never hurts. But theoretically, you can just kind of throw shit together and hope for the best. So these are probably the dominant form of coupling agent. And when companies do peptide synthesis, especially companies that aren't really chemistry companies, they will use the uraniums because they're very, very tolerant of sloppiness and mistakes. So how do they work? Well, it's weird actually. First thing is they react with themselves. So what I drew is what you have in a solid when you buy this stuff. It's not actually the reactive species. You think, well, it looks relatively reactive to me. And I agree, it looks relatively reactive to me too. And I think that's what they were, like, the people who invented these went, yeah, it'll react just directly from the thing, but it doesn't. So draw zeros in different color. Huh. I think I just deleted everything. Oh, silly. Sorry. If you're ahead of me, you can try and draw out the product though. And then the other guy. So this isn't going to be particularly stable immediately because we've got this whole charge disparity between these two molecules. Notice one is negatively charged and one is +2. Actually, one's +3. So we can resolve this pretty quickly by just having this guy do the same chemistry on the guy we just had. So we end up with 2 times. Now I've drawn these as discrete steps. They probably all happen more or less at once because none of these charged species make a lot of sense. And we still have a PF6 minus. So we made this new species here. And what we've done is we basically transferred this guanidinium from the nitrogen to the oxygen. And that's because it's a little bit more stable on the oxygen in solution. That's it. Is this particularly important for the mechanism? No. It's a thing that happens. But now if what we do is we take that molecule, this is important for the mechanism. I'll treat that with a carboxylic acid. Now note that we have base present for this. So we have DIPEA. Why do you think we're using DIPEA for this reaction rather than, triethylamine? What's the advantage of DIPA over other bases?
It's more hindered.
Yeah. It's the most hindered you can make an amine base. You can't make triisopropyl. Because you're going like, well, okay, why is it not triisopropyl? You can't make triisopropyl amine. I don't think triisopropyl amine exists. I'm just gonna, and if it does, it's really, really, really difficult to synthesize. I'm just gonna look this up. Propyl. Okay, it is available from Sigma. Just curious how much it costs.
I was going to say because the more it costs basically means the harder it is to make.
Yeah. Okay, so that part number has been discontinued. Okay, it's $200 for 50 milligrams.
Huh.
Whereas I can buy, 4 liters of diisopropylamine for the same $200. So when you're buying 50 milligrams at a time, it is not particularly useful. And it's a custom synthesis. It's because it's really, really hard to make, because it's really hard to get 3 isopropyl groups around a nitrogen. So this is about as hindered as you can get. And again, yeah, maybe you can buy the triisopropyl, it will be better for this, but nobody's got that kind of money. You go through tons of this stuff. So this is going to deprotonate the carboxylic acid really easily, because that's what bases do. So if I draw the solution of that, we'll have that. And then this can now attack the uranium. We'll just draw the tetrahedral intermediate for a second. So we have that. That poor carbon is now making 4 bonds to heteroatoms. That's not a thing. Like, there's an example in tetrodotoxin, pufferfish toxin, where there's a carbon that makes 4 bonds to heteroatoms. But that's about the only example I can think of, and it's in fast equilibrium with a whole bunch of rings that it forms. So this doesn't last very long, and we lose the uranium. So what you need to do is you need to make sure that you're losing something that's even a better leaving group than a carboxylic acid, and uranium is one of them. And so now we can sort of see where HATU and HCTU come into their own here. Because this thing is the same for all uraniums. And this varies. So HATU has a nitrogen here, which pulls electron density out of this system, which makes this a much better leaving group. HCTU has a chlorine here, which pulls electron density out of the system, making it a better leaving group. So both HATU and HCTU accelerate this step. The acid reacting with this thing, forming a tetrahedral intermediate, and ensuring the tetrahedral intermediate breaks the way we want. Both HATU and HCTU increase the amount of this, whereas HBTU, you can go backwards. You can go back to carboxylic acid plus uranium, so it doesn't necessarily activate all the carboxylic acids at once. HATU basically does. HCTU is kind of like a 90-10, mostly activates them. And that's why HATU is more reactive. Because this piece here is the same no matter whether you start with HATU, HBTU, or HCTU. So reactivity comes in from this activation step. Now we react this with an amine. So another amino acid, for example. And if we're thinking about this, again, we're not very creative. The driving force is formation of urea. Tetramethylurea. An amide bond after deprotonation by the base, because it'll be an NH2 initially. It'll be a positively charged nitrogen initially, and then immediately deprotonate. That's more reactive than carbodiamide. Now, why might you not want this to be the most reactive thing you can have? And that's because, let's consider a problem. So racemization, it's not two C's. Is when we have take a base, and then we reprotonate from that base. Of course, that is flat now, and so %50 returns to product, which is great. But the problem is 50% has become the wrong enantiomer. So this is not a problem with carboxylic acids. And that's because, you know, if you have a carboxylic acid, what's acidic? It's the acid, not the alpha proton. And so you don't deprotonate the alpha proton. It's a big problem for activated esters. It's a big problem for ketones as well. And when we're thinking about it, what we want to do with an activated ester, the entire point of an activated ester is to make this more electrophilic. Right? It's to make that carbon more positive. That is why we are using an activated ester. We want to increase the attack on that carbon by making it more positive. Of course, what that does is it makes the alpha proton more acidic. So the better an activating group you have, the more acidic the alpha proton is, the bigger racemization is going to be a problem for you. And that's just the way it is. There's no way around that simple problem of physics. But this is not actually the main, what I've drawn there, this racemization is not actually the main issue on how these things racemize. Mostly what we need to worry about is when we have a dipeptide or bigger. So this is why okay, so let's say we do this. We have an activated ester like this. Deprotonating here is possible, but it's not actually the major mechanism. The major mechanism of problem is things love making rings. You just made this a really good leaving group. Thank you very much. I am going to make a ring. Now, if we count the atoms, 1, 2, 3, 4, 5. We've got a 5-membered ring. It's the fastest ring to form, period. I'm going to add an L into this. know, when I'm rotating things, I have to take that into account for what the right stereochemistry is going to be for my groups. Now we've got a problem. Because if we think about this, sp2, 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 4 pi electrons. So we have 4 pi electrons. Is that aromatic or anti-aromatic? If it made an aromatic ring. Sorry?
Anti.
Yeah, it's anti-aromatic, right? So it's unstable. But it's okay. We're not aromatic, right? We are missing that the final component, which is we need to have everything all in a ring. And we have an sp3 carbon in a way. However, if we remove that proton, how many pi electrons will we have?
6.
6, so it's aromatic, right? And everything will be sp2. So that proton went from being pretty acidic to stupid acidic. Because if all I can do is remove that proton, I can have resonance. I can have a fully aromatic ring. And nothing is more stable than fully aromatic rings, really. Now, there are some problems with it. It's not the best aromatic ring because it's got some weird bonds. But any base, triethylamine is great for this. Can break that bond. Then what do we have? And if you'll notice, we're fucked at this point because we have now made this center sp2. This is aromatic. You can compare with furan. It's kind of like furan. This is still attached to a hydrogen. I've arbitrarily removed the hydrogen. That's wrong. Should have an H on here all the way along. So now we have an issue because now we can, of course, attack from either the top or the bottom face. If this goes H plus, and suddenly I've scrambled that center. So if I have my new nucleophile, my nitrogen from my amine, this is the other amino acid. It attacks. Sorry, that nitrogen's been positive the whole way through. It attacks, and then we regenerate our peptide. So we have this big problem now in that this is a mix. So whether we made the peptide from the amine directly attacking the activated ester, giving us the right stereochemistry, or whether it makes us oxazoladinone. So this is just an oxazole. Or whether it makes us oxazole and then reacts on that, we're not gonna be able to really know, right? We're just gonna have to start scrambling of that enantiomer, of that stereo center. And so we need to prevent this happening. Because if this happens, we're in trouble. And this happens anytime you have an amide adjacent to an activated ester. So next class, we're going to start by talking about how we avoid this problem. Because what it does, of course, it gives you random stereochemistry. And if you're trying to make a peptide that has biological activity, the stereochemistry of the side chain is important because biology is chiral. And so if you make the wrong enantiomer or wrong diastereomer of the overall peptide, because you have like a random thing in there, you're going to have molecules that are not going to be active. You're going to have molecules that do the wrong thing. You're going to have just a mess. And so I can't actually think of any example where racemization is good, because normally you put an awful lot of effort to making one enantiomer. I don't know why you would ever want to really racemize, but it's really bad for peptide chemistry and for drug development. So we need a way around this problem. And it's intrinsic to the fact of having an amide bond adjacent to an activated ester. There's no way around that. So we need to avoid that situation. Okay, I think we'll continue next class on this then. And have a good Monday.